Okay, Assalamualaikum and good evening to all of you. Okay, so how are you everyone? Can you give me a response? Okay. So, okay, thank you. I hope everyone is in a good health condition and emotionally stable. Okay, inshallah. So, please do not hesitate to inform if you have a problem. Okay. So, alright student, today we will learn about gas absorption. Okay, we will learn about gas absorption, chapter 4. Okay, so this is the last chapter in this subject. So I hope everyone will pay attention so that you can understand, okay? And I will randomly pick someone to answer my question, okay? So please pay attention. Alright, before we start, I just want to give a few words of encouragement. So this is a doa, okay? A doa for us to ask Allah to give us strength to be patient. Right? So, Rabbana afrik alayna sabran wa tawaffana muslimin. Okay, in this situation right now, during this pandemic COVID-19, I feel that we need this dua, right? So may Allah strengthen the passion of all of us in facing this trial. Okay, inshallah. Okay, so before we start, we also have to know the course learning outcome. So this chapter, gas absorption, will consist of 6 subtopics, okay? 4.1, 4.2, 3, 4, 5, 6, okay? 6 subtopics. Alright, so for 4.1, the definition, application, and notation used in gas absorption. Also, we recap back on Raoult's law, on the equipment and description for gas absorption. And you will also learn on pack tower, okay? Packing material, the characteristic and geometrical shape. And the last one is the multi-stage counter-current operation. So this one is just similar with the one that you learn in LLE, liquid extraction, and also distillation, right? Okay, you will find the stages by using the graphical method. Okay, this is the last subtopic you will learn. Right? So this is the course outcome. Right? You have to justify the concept and application of mass transfer in separation process. So this one is regarding your Aspen Plus simulation. Okay, where you have to respond to the experimental and simulation outcome. All right. So this is the lesson outcome, okay, in this chapter. Okay, you should be able to define gas-liquid equilibrium. Okay, so since the topic is gas absorption, right? So you will have two phase, which is gas and liquid. Before this, you learn on LLE, right? So both is liquid, but now it is gas and liquid, all right? Okay, then you should be able to differentiate between pack and plate tower. Next is explain packing material. Okay, explain packing material and flow arrangement in pack tower. Next, calculate pack tower diameter and height of an absorption towers. Okay. The last one, you should be able to demonstrate the material balance and calculate the number of theoretical stages in a multi-stage counter-current operation. Okay. Alright, that's all for the course learning outcome. Okay. So this is an example of gas absorption, okay? Gas absorption application in industry. Right. Just to show you the overview of the gas absorption. Okay, now we move on. What is gas absorption? Okay, gas absorption, or also known as scrubbing, okay, also known as scrubbing, is an operation in which a gas mixture, okay, you will have a gas mixture. I can denote it with A plus B, okay, where your gas mixture is contacted with a liquid. This liquid, or we call as solvent, okay, your solvent. The concept is quite the same with LLE, okay? Just the phase is different, okay? Gas and liquid. For the purpose of preferentially dissolving one or more component of the gas mixture and to provide a solution of them in the liquid. Alright, maybe you cannot see. It's okay, I will draw for you. Right, for example, you have a towel, okay? Right. So at the bottom, you will have a gas inlet. Gas in. This is your feed. Okay. I denote it with A plus B. So A component is the one that you want to remove. Means that you want A, you doesn't want B. Okay. So you have to separate A from B. You are using gas absorption unit. Right, so this is the gas inlet, so it will be contacted with your liquid. Okay, you have liquid here, or we call as solvent. Okay, so your gas will interact with your liquid. Then you will have gas out here. You will have gas out here, or we denote it as raffinate. Okay. But please don't confuse with LLE, because in LLE we also use a raffinate term, right? Okay. So another product you have is liquid out. So at this stream, you will have your A plus your C. I consider solvent as C. Okay, so this is the one that you want to remove. You want to separate A and B, right? So your A is in the liquid outstream. Sorry. Okay, so in this raffinate, there will be more component B here. Okay, you want to separate A and B, right? So B component, more B component here, and more A and C component here. Right? So since your gas, from the bottom will flow upward. Okay, this is gas. So your liquid will flow downward. Alright. So there is a contact between your liquid and gas here. Okay. In this tower, there will be a contact of your liquid and gas in counter current direction, right? Counter current direction means that gas upward direction, liquid downward direction. Alright. Okay. Gas in feed. Okay. Okay, so I want to ask question to test your understanding. Okay, can I pick? It's okay, there is no wrong or right answer. I just want to test your understanding, okay? Alright, wait. Okay, Syakir Naufal. Okay, Syakir. Based on my explanation, here, okay, in a simple word, what do you understand by gas absorption process?
There is a liquid in and then there is a gas up.
Okay, actually in gas absorption, you want to separate what? Syakir, Nafal?
Liquid and gas.
Liquid and gas. You want to separate A from B, right? Okay, you want to separate
Yes.
A from B, right? Okay, thank you, Syakir. Okay, maybe another person. Hmm, it's okay. Just try to test your understanding, right? Okay, Nurul Iza Zuraini. Nurul Iza Zuraini. What do you understand from my explanation here? What is gas absorption?
Um, same concept with LLE.
Okay, can you elaborate a little more?
To separate uh,
Okay,
one solvent become
okay.
another.
Okay, your gas inlet will have component A and B, right? So your component A and B will contact with what?
Yes.
Okay, your gas A and B will contact with what component? Component C, right? Your solvent, right, Iza? Okay.
Yes.
So it will produce two outlet stream where more component A here, right? So this is the one that you want to separate. All right, thank you, Iza. Okay. So, all right. Okay, we move on to definition and application of gas absorption. Okay. So gas absorption is mass transfer operation in which one or more species solute is removed from gaseous stream by dissolution in a liquid solvent. Okay, this just repeat back what I have teach. Oh, I think. Oh, okay. So this one just want to say about the mass transfer. Okay, we will have a mass transfer from gas phase to the liquid phase. Okay. The solute so transferred is said to be absorbed by the liquid. Okay, so your liquid, your solvent will absorb the component A, right? Okay, the process of gas absorption does involve the diffusion of solute from the gas phase through a stagnant or non-diffusing liquid. Okay, so that's all for this slide. Okay, this one we want to show some example of a gas absorption application. Alright, so solute here mean your A. Okay, the insoluble component present in the gas which is not absorbed is called the carrier gas. So this one is your B. It means that your solvent C will only absorb solute A. Okay, but it will not absorb solute B. Right? So then you will have A plus C here and more B component here, right? So you must choose a good solvent or you must choose a solvent that can only absorb A, okay? You cannot choose solvent that can absorb A and also B, so it's difficult for you to do the separation, right? Okay, so the transfer is based on the preferential solubility of solute in the liquid, okay? The mass transfer depend on the solubility of your solute A in solvent. Okay, so this is some example. Removal of hydrogen sulfide. So this one is your solute A from natural gas carrier. This one is your B, right? Okay. Using suitable solvents such as an aqueous solution of an alkanol amine. So this is considered as your component C. Okay. An intimate contact between the gas and the liquid is achieved in suitable equipment or device like pack column, tray column or spray tower. Okay, so the reverse of absorption is called desorption. Okay, this one for this one we just want to give you the knowledge, but in this subject we will focus on absorption. Okay, we will focus on absorption. So the suitable device or equipment, so I mean this one, okay. So this is example of the device. Okay, we will look further into the equipment in other subtopic. Okay, so far can you understand?
Yes, madam.
Understand, madam.
Understand.
Yes, madam.
Okay, thank you guys for the feedback. Okay, so this one is just the application. So you can look the gas absorption application, for example, in removal or recovery of ammonia, okay, in fertilizer manufacturing or control of sulfur dioxide from combustion source, or removal of carbon dioxide from air. So gas absorption is a very important separation process, okay, in our life in industry. Okay, so this is important term that you have to remember, right? It's okay. I have draw. Okay, I have draw here, right? So this will be your feed, solvent, or we denote as absorbent. Alright, so your liquid out, more component A. So same as LLE, we call this as extract. Okay, and this one is raffinate. Okay, so you have feed, where your feed will be contact with your solvent, then it will produce raffinate and extract. Right? Okay, so this is the feed, the gas mixture which to be extracted. So this is your A plus B. Your solvent, where the is the liquid which the feed is contacted. So this is your C, extract the solvent rich product. Okay, you will have A plus C here. And your raffinate, the residual gas mixture which solute has been removed. Okay, you will have B here, more B component here. Okay, so this is the most widely used solvent, such as water, hydrocarbon oil, and aqueous solution of acid and base. Alright, so we want to go about ideal solvent. Okay, how to choose an ideal solvent? So this is the criteria of ideal solvent. So it must has a high solubility. Of course, this one is very important because our solvent will absorb the component A, right? So it must have high solubility for the solute. Okay, it must has a high solubility for the solute. All right, to minimize the need for solvent. Okay, so if the solubility is higher, so we doesn't have to use more solvent, right? Okay. Then it also has a low volatility in order to reduce the loss of solvent, right? Of course, it also should be stable to maximize solvent life, right? So this is also important, non-corrosive, okay? Non-corrosive to permit use of common material of construction, all right? Low viscosity to provide low pressure drop, non-toxic and non-flammable. Okay, and of course, this one is important. The solvent must be available. Okay, must be available. And also in costing and in economy, in an industry will choose the cheap solvent and of course commercially available solvent. Alright, so far, okay guys?
Okay, madam.
Okay, so, okay, thank you. Okay, this one we want to go for gas-liquid equilibrium for ideal solution using Raoult's law. So this one we have learned, right, in mass transfer. You have Raoult's law. So we will recap a little bit about Raoult's law. Okay, so in any mixture of gases, the solubility of each gas depend on partial pressure. Partial pressure is the small p, okay? Partial pressure is the small p, okay? You can see here. Small p, partial pressure of A in vapor phase. So, XA is your, sorry guys, SA is your mole fraction, right? Okay, mole fraction of A in liquid phase, okay? X liquid. So, capital letter P mean vapor pressure of pure A at certain temperature, okay? Alright. Okay. Actually, this one, if you can remember, I also have touched on mass transfer on the last subtopic, interface. Interface mass transfer. Okay, interface mass transfer, the last subtopic in mass transfer chapter, okay? So, but it's okay. It's good we recap back the knowledge, because this one you have to understand in order for you to understand more about the gas absorption. Okay, because gas absorption apply this to film theory gas liquid system. Okay, to ease your understand, I label here, this one is gas, okay, this one is gas. So this one is the interface, okay, interface. Okay, this one is the interface, and at this left side is your liquid phase. Alright. So, assuming solute A is diffusing from the bulk phase G. So this, okay, this one. Your solute A from the bulk phase G. G means gas, okay? G means gas. Okay, so A is diffused from gas to the liquid phase. Okay, from gas to the liquid phase. Okay, the direction is like this. From this one to this. Right? So it must pass through phase gas. Okay, it must pass through phase gas. Then it must pass through the interface. Interface mean here, right? Okay. Then it must pass through phase L, phase liquid in series, right? So as you can see here, your gas, your bulk phase gas, KYAG, okay, it will diffuse to the interface denoted as YAI. So I here mean interface, okay? Interface of gas. X is for liquid and Y is for gas. Okay? Alright. So this is the gas interface. So when it enter the liquid phase, it will form the interface in liquid. Okay, XAI. Okay, X is liquid at interface. Then it diffuse till the liquid phase. Okay, so it's like that from YAG to YAI, then XAI, then the last one is XAL. So basically it diffuse from gas to liquid. Okay, concentration gradient must be exist to cause this mass transfer through the resistance in each phase. Of course, if you can remember back in mass transfer, in order for mass transfer to occur, so there must be a difference in concentration gradient, right? Alright, I want to ask you, okay, based on your understanding on mass transfer, okay, that we have learned, a component will move from a high to low concentration, or from low to high.
If I'm not mistaken, it will be high to low.
High to low, right? Thank you. I cannot see who's answering. Okay, thank you for your answer. Yeah, it corrects this one. Okay, it will be transferred from high to low concentration, right? Okay, so the concentration in the bulk gas phase decrease. So as it diffuse, so mean at YAG we have high concentration, right? Since it will move from high to low, right? So high concentration, okay, the concentration in the bulk phase YAG decrease to YAI at the interface. Okay, YAG to YAI, the concentration will decrease at the interface, alright? At the interface, liquid concentration XAI, at interface fall to XAL. Okay, basically just want to tell you this one, okay? From YAG, so it moved to the interface of vapor, then interface of liquid, then to the liquid. Alright. So far, okay? Any question, guys?
Okay, madam.
Madam.
So far, no
Okay,
question.
madam.
Okay, thank you, guys. Okay, so this is the last for 4.1, okay? Last for 4.1. So from this diagram, we can interpret into this graph. All right. So as you can see here, P here is your bulk phase, your YAG. Okay. Your YAG here. Okay. If you go downward, it is your YAL. All right. So this one just want to show you the point P and M. Okay. M is the interface. Okay. M is the interface. So you can see at interface, you will have XAI, right? I mean interface, right? So if you go to the right, to the left, you will have YAI. Okay. At interface, you will have XAI and what? YAI. Okay. So this is meant by this graph. Alright. So point P is your bulk phase. The composition is YAG. Okay, the composition is YAG and XAL here. Okay, so for point M, YAI and XAI. Okay, YAI and XAI. So this one for this slope is actually applying the mass transfer coefficient. Okay, this one we will learn in other subtopic. Alright, okay guys. Any question before we stop for 4.1? Okay.
Okay, madam.
Alright. So, okay, thank you guys. We have finished for 4.1. So, we will continue with 4.2. So, you can have a break for 5 minutes, I think. Alright. Okay, thank you guys.
Okay, thank you, madam.
Okay.
Madam.
Give me them.
Alright.
Thank you, madam.